to Gas Laws Notes Part 2. So we just went through the combined gas law, and let's now look at Dalton's law of partial pressures. This is a really easy one. It just says that each gas in the mixture creates pressure as if the other gases weren't there. So they aren't interacting with each other, which follows the kinetic molecular theory. The total pressure is the sum of the pressures created by gases in the mixture. So whatever gases you have, say in air you have oxygen, nitrogen, carbon dioxide, etc., the pressure from each of those adds up to get the total. The pressure each gas exerts is called its partial pressure. And this comes from John Dalton of atomic theory fame. He studied meteorology, so he was very interested in the atmosphere. So here's an example. If you've collected 40 milliliters of hydrogen using water displacement, and you've got a temperature of 22.5 and a pressure of 745 millimeters of mercury, water vapor is mixed in with the hydrogen when you collect it. But you want to know about the hydrogen by itself, so you want to know what pressure can be attributed to just the hydrogen. So we need to figure out what the total pressure is of that system, and then subtract out whatever we can that's caused by the water vapor. Well, we have the total pressure, 745 millimeters of mercury. Now we know what the temperature is, and I believe this link, well, it's not a link. We have to look up on a water vapor pressure table, which we have in the back of our book, and we'll have in any lab that we need. It says that at 22.5 degrees Celsius, the water vapor pressure is 20.4 millimeters of mercury. So all you have to do is subtract it, and you get 724.6 millimeters of mercury from just the hydrogen. So all we've done is looked up for a given value and subtracted it out. And this is the most common way we'd have to use Dalton's law, is when we have to deal with water vapor that's mixed in with the collected gas. All right, now let's look at Avogadro's principle. Avogadro of mole fame. So these guys do more than one big idea usually. So he proposed an idea, actually it led him to the idea about moles, that his idea was that equal volumes of all gases of the same conditions, temperature and pressure, contain the same number of particles. Sort of a way of counting the number of particles, because he understood that with enough space between them that it wouldn't matter how big the particles were, just how many there were, and that would determine their pressure and their temperature. So an extension of that is Avogadro's principle, in that 1 mole, Avogadro's number, of any gas at standard temperature and pressure occupies a volume of 22.4 liters. That's a pretty useful piece of information. So make sure you highlight that or something. 22.4 liters at STP. 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure, which of course can be measured in different units. So an example of how we might use that is to figure out the volume of a certain mass of a gas at a certain temperature and pressure. Now Avogadro's principle gives us a volume at standard temperature and pressure for 1 mole of gas. So let's find out how many moles of gas we have for neon. We have 7.17 grams of neon, and its molar mass is, the molar mass of neon is 20.2 grams in 1 mole. That gives us Got my calculator. Hopefully you've got yours too. 7.17 divided by 20.2 is 3.5, I'm sorry, cross that out, 0.355 moles of neon. So now if we know the moles, I'm going to clear that so I have a little more space to work. Point 355 0.355 moles of neon. Now we can use that to find the liters at standard temperature and pressure. So 1 mole has a volume of 22.4 liters, and that gives us 7.95 liters at standard temperature and pressure. Okay, but that's not what the question asks. The question asks for something at 24 degrees and 1.05 atmospheres. So what we have, let me summarize. We know that we have a volume of 7.95 liters at a pressure of 1 atmosphere and a temperature at 273 Kelvin. That is standard temperature and pressure. What we want to know is V2, that's our question, at a pressure of 1.05 atmospheres and a temperature at, let's see, 273 plus 24 is 297 Kelvin. We have 2 sets of information, temperature, pressure, and volume. We would use the combined gas law. You can put that in, plug and chug, and you should get 8.25 liters. So just to recap, I did this in steps. I wanted to find a volume of a certain mass of a gas. So I needed to know moles. You always have to work with moles. So if you have grams, change it to moles. From there, I could use Avogadro's law to find the volume at a certain temperature and pressure, STP, and then I modified that to be at a new temperature and pressure. There are other ways of going about doing this problem, but with the tools we have right now, that way works. All right, so this last relationship is a really important one because it allows for you to solve problems such as what we just did in a more straightforward way because it puts all the variables together in one equation. The combined gas law has 3 of the 4, but given that the amount of gas isn't included, then it doesn't cover all bases and you need a comparison ratio. What we're going to do is put them all together, and what you find is that pressure, volume, divided by moles and temperature gives you what you call the ideal gas law constant. That's what R is. It's that K we've been talking about, only it's specific to a certain set of units, but it's good for all gases under all conditions. So the ideal gas law constant has several values depending on the pressure units you use, but the more common ones are 0.0821 liter atmospheres per mole Kelvin and 8.314 liter kPa per mole Kelvin. Different numbers because of the different pressure units. Okay, So here's how we might use something like this. We would do it for a stoichiometry problem if we wanted to find out the volume of a gas at a certain set of conditions. We could do it using Avogadro's law and then the combined gas law, but this is going to save us some time. So in this example, ammonium sulfate can be prepared by a reaction between ammonia gas and sulfuric acid. There's the reaction. Now we want to know what volume of NH3 measured at a certain temperature and pressure will be needed to produce 5,000 grams of ammonium sulfate. Okay, so here we have a mass of one substance, and we need to find the volume of a gas. This is typical of how you might find a stoichiometry problem using a gas. So I've copied this onto the next page so I have a little room to work. All right, so let's record what we know. We have 5.00 times 10 to the third grams of ammonium sulfate. We want to know liters of ammonia at a temperature of 78 degrees Celsius and a pressure of 1.66 atmospheres. All right, the link between two substances in an equation is always via moles and their mole ratio. So let's start just by doing some stoichiometry. So 5,000 of NH4 to SO4, and we need to change that to moles. So the molar mass is, I quickly add it together. Hoping my memory is serving me correctly, and I believe it is 132.1 grams per mole. Grams cancel out. Since I want to know about the ammonia, I'll do a ratio of 2 moles of ammonia to 1 mole of NH4 to SO4. And those cancel out. So that will give me moles of ammonia, which then I can use in the ideal gas law. So I don't have to go all the way to grams. So I've got 5,000 divided by 132.1 times 2. I calculate that I get 75.7 moles of ammonia. Okay, oops, sorry. But now I want to know the volume. So here's where the handy dandy ideal gas law. So we could say how many liters of this at standard temperature and pressure and then do the combined gas law. But I think you'll agree that this is a slightly shorter method. We know that PV PV equals nRT. That's the ideal gas law ratio. If we want to get V by itself, I'm going to divide both sides by P. And I can solve for my volume knowing moles, which I know, a gas law constant, which I gave you a little bit ago, a temperature, which we have, and a pressure. So the volume is going to equal 75.7 moles. Now, which R value are we going to use? We have a pressure of 1.66 atmospheres. So the R value with atmospheres was 0.0821 liter atmospheres per mole Kelvin. And the temperature is 78 plus 273, 351 Kelvin. all over a pressure of 1.66 atmospheres. So, if you notice, I'll check the units. My atmospheres cancel out, my kelvins cancel out, and my moles cancel out, leaving me with liters, which is the unit that I want for volume. So volume equals, please check my math, 75.7 times 0.0821 times 351 divided by 1.66. I get, with keeping 3 sig figs, 131 liters. No, I'm sorry, 1,310 liters of ammonia. There you go. Using the ideal gas law to find the volume of a gas at a certain temperature and pressure and number of moles. All right. This is the gas law song, which I will be sharing with you tomorrow. I don't have the music soundtrack with me. I hope you have a good night and talk to you soon.